Okay, so as we've been saying, we were looking at the solution to the homogeneous differential equation, linear differential equation with constant coefficients. We've been doing second order ones. And what we said, let's just write this in a fairly general form, d second x, second order. We had this one written as omega naught over q for this coefficient times the first derivative and omega naught squared times x equal to 0. And this was the equation in a sort of generalized form that we've been working on. And we said that you could write solutions to this in various forms depending on the value of q. And what we said was that if q was less than a half, then we could write the solutions x of t as some constant e to the minus alpha 1t, another constant k2, e to the minus alpha 2t. This is for the case of q, dimensionless number being less than a half. And in the case where q is greater than a half, it's convenient to write this in the form of some other constant k times e to the minus alpha t times the sinusoidal function, cosine of some omega t plus phi. In this case, the alpha is a positive number in each case, and the k1 and k2 would just be things that are constants that are determined by the initial or boundary conditions. And similarly, in this case, in this form, k and phi are the two coefficients that we would have. For the case where q is a real number, these things always decay to 0 with time. Q is a measure of how fast energy is removed from this system in practical physical systems. Okay, so what we learned in differential equations then was a more general thing, which I want to talk about now. In a differential equations class, they said, well, suppose we put an arbitrary function on the right-hand side. That turns it into a non-homogeneous differential equation. And there was all this talk about the forms of f of t that we could have and how to solve them. And the gist of it is that the general solution for x is a superposition of something that depends a lot on f sub t plus a mix of these guys, and we get some new constants. For our purposes, we're really going to focus almost exclusively on one function, which is a sinusoid. So sinusoids are the basis for almost everything we do. And I'm going to write it in a fairly general form. I'll put a constant f out front and call it e to the j omega t. So this is a generalized sinusoid. And for reasons that are known only to me, it's convenient to just write s here. It just simplifies all the stuff I have to write. So I'm going to write it as st, but whenever we get the urge, we're just going to let s equals j omega when it's convenient to write things that way. All right, here's an important principle, big deal here, and that is the following fact. For a linear system, constant coefficients out here, if we have that, and if we put in a sinusoid as the input at a particular frequency omega, then the ultimate solution to this thing, when it reaches steady state and these parts die out, so these decay, if we put in a sinusoid at a frequency omega, the steady state response of this system will be an oscillation with a frequency of omega. And if it's a linear system, then you'll get no new frequencies. And as we'll see, if you get new frequencies, that means it wasn't a linear system, or these were somehow time varying or amplitude varying. So we'll see that those two things are necessary. At any rate, what we need is we're going to try and put in a sinusoid to the system. We'll let the initial conditions do their thing, but assuming this is a so-called stable system where Q is positive, this stuff will die out and we'll get a steady state response. And we can characterize that. I'm just going to plug into the formulas here. If we take the second derivative of this, so the solution is going to be, in general, is a constant A, which is going to depend on S or J omega, times the complex exponential out here. So our solution is going to be e to the j omega t, or we'll write it some a of s times e to the st, again for convenience. And the convenience is going to start now. If I take one derivative of this guy, let's just put this in. So I got omega naught squared times my x function, which is a e to the st st, and that's going to equal f e to the st. And then over here, I'm going to get omega naught over q. We take one derivative of this guy, one factor of s comes out, and everything else is the same, a e to the st. And I didn't leave myself enough room over here, but I think we'll be all right. And the second derivative of this guy brings out a second factor of s. The a is still there, e to the st. And I believe this is the, put a plus sign in there, and I believe this whole thing then is what we got out of this with this right-hand side function. But here's the deal. This a, and for that matter the st, all factor out. So I can rewrite the left-hand side of this thing as a e to the st, whatever all that is, and I have my familiar polynomial back inside the brackets here, omega naught squared. And on the right-hand side, we still have f e to the st. All right, so if we wait long enough, this will become the solution for appropriate values of a. So all that's going to happen here, we put in a sinusoid at a frequency s equals j omega. So omega is the frequency of our sort of test input sinusoid. We're going to find the frequency response, which is one of the most important things we're talking about. We're going to find the frequency response by letting omega vary. And what's going to happen is, in each case, when it reaches steady state, the only thing that's going to change is for each value of omega, we'll get a different value of a. So let's solve for a. First of all, we can get rid of all the e to the st terms, and it gives me the following formula. Let's write it kind of big deal here. A as a function of st, which could have been j omega t, is equal to f divided by s squared plus omega naught over q times s plus omega naught squared. And that's a big deal, all right? So a is going to tell us the magnitude of a is going to tell us the magnitude of the sinusoidal response to this input, and we can find the magnitude and phase of this. We can do this later. We're going to learn a lot about how to do these things very efficiently. I'm just going to write the solution down for s equals j omega. If the frequency is very small, that means that s equals j omega is small, and certainly j omega squared is even smaller. These two terms for sufficiently low frequencies drop out, and this thing is proportional to, so if I make a log-log plot, as we like to do, of the magnitude of a of j omega as a function of j omega, at low frequencies, this thing will be whatever f is divided by omega squared. We'll put in, practical values as we get to it, but just like in a math class, we're ignoring all the practical stuff right now. At high frequencies, very high frequencies, so for sufficiently large values of all of this stuff, the s squared dominates, and these other terms are not important. Well, s is proportional to omega, so s squared is proportional to omega squared. At high frequencies, this thing on a log plot just goes inversely proportional to 1 over omega squared. On a log of this axis, that just makes a straight line. As we will see then, this thing has a so-called low-pass characteristic. At low frequencies, it has some gain. At high frequencies, it drops off. We'll say more about this, but the thing that we'll see later is, depending on the value of q, and here's an important thing, we're talking about resonance for a lot of these things. If the value of the input frequency is close to the center frequency, this omega naught, then you get a different response. You get a strong response. If q is rather large, then we get a very strong response at frequencies close to omega naught. Omega naught is called the natural frequency of the system, and again, these are characteristics of the left-hand side of this. With a simple, we can characterize this using frequency domain things. So this is for high values of q, by which we mean much, much greater than a half. If q is closer to a half, then we'll get something like that, smaller q. And if q is really small, then we'll just get this kind of droopy response with 3 segments in this response. Well, we'll say a lot more about these things. We'll learn how to do all these things as we go along, because that's really the stuff I wanted to talk to you about. But what we've done here is just made the connection between all this math that you learned. I've tried to simplify it. We're only going to look at the sinusoidal response, and eventually we're back to a way of characterizing the response of a linear system by testing it with a series of, a set of frequencies. And that's the frequency response. All right, so we'll talk about this a lot more as we go along.